The third alien visitor is closer than you think. You know Oumuamua and Borisov. Now there's a third outsider barreling through our backyard, 3I Atlas. It's on a strange orbit, it's showing weird chemistry, and yes, some people claim it isn't natural. Here's the simple version you've been looking for: what 3I Atlas is, what it isn't, and what Avi Loeb actually gets right or wrong about it. There's one detail that could flip the entire debate, and we'll get to it after we lay the groundwork. Okay, so basically, what are we even looking at, and how do we know it came from beyond our solar system? What 3I Atlas actually is, the basics. Okay, so basically, 3I Atlas is the third confirmed interstellar object ever found, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The I stands for interstellar, and the 3 marks its place in this tiny, history-making list. The Atlas survey, the Asteroid Terrestrial Impact Last Alert System, spotted it first, tagging it as C2025N1 Atlas before follow-up observations nailed the key feature. The orbit is hyperbolic. In other words, it's not bound to the Sun, it's just passing through. Here's what that means in plain terms. Most comets and asteroids loop the Sun on ellipses, think stretched circles. If you plot their orbits, they close on themselves and come back. A hyperbola is open. It's a one-and-done slingshot. Mathematically, that shows up as an eccentricity greater than 1, and dynamically, it shows an excess incoming speed that the Sun's gravity can't cancel. When astronomers measured 3I Atlas's path, they saw the telltale signs: an interstellar incoming velocity and a trajectory that never settles into a loop. That screams from outside. Why does the speed matter? If something's moving faster than the local escape velocity when it's far from the Sun, gravity won't capture it. Even if the object dives deeper in and whips around the Sun, it'll still exit the solar system with leftover speed. That's what we saw with Oumuamua and Borisov, and now again with 3I Atlas. Add in the inclination, the angle between its path and the plane where most planets sit, and you get another clue. Interstellar visitors tend to come in at odd angles, not neatly aligned with our planetary disk. 3I Atlas fits that pattern. Everything clicked when observers noticed activity, a coma and hints of a tail around the object. That means it's releasing gas and dust as sunlight warms it, a classic comet signature. But the nucleus itself, the solid heart of the comet, is hard to measure because the surrounding coma swamps the light. So size estimates are fuzzy. The simple version is, it's small by planetary standards, bigger than a rock, and active enough to be bright for decent telescopes. Here's what most people miss about the discovery timeline. Surveys like Atlas scan the sky repeatedly, looking for moving dots. The trick is cadence, how often you revisit the same patch, and sensitivity, how faint a thing you can see. Interstellar objects are rare, faint, and fast. You need quick follow-up to link dots into a track and compute an orbit. In the first days, there's always uncertainty. Is the motion consistent with a bound comet with a weird orbit, or unbound and interstellar? With 3I Atlas, within a day or so of detection, the orbit solution leaned interstellar. More data tightened the fit and removed the ambiguity. Okay, but how do surveys actually catch something like this? Think of a nightly grid of images. Software flags anything that shifts between frames. Most hits are near-Earth asteroids or known comets. New movers get provisional designations. Then the math people jump in. You feed positions and times into an orbit solver, and it spits out a best-fit path with uncertainties. If the best-fit path is hyperbolic with statistically solid residuals, you've likely got an interstellar visitor. Biases matter too. We tend to find objects that are bright enough, slow enough to track across multiple nights, and well-placed relative to the Sun from Earth's viewpoint. That selection affects shapes which interstellar objects we notice. Brightness behavior is another early clue. As 3I Atlas approached the Sun, its brightness increased as expected, but the rate and color hinted at unusual chemistry. We'll keep the details simple for now. Telescopes reported strong signals from carbon-bearing molecules and a coma that turned on at distances where typical water-driven comets are still quiet. That suggests CO2 or CO, supervolatiles that sublimate at lower temperatures, might be driving the activity. This lines up with observations reporting 3I Atlas as rich in carbon dioxide, with some water ice and vapor, carbon monoxide, and carbonyl sulfide in the mix. That's already interesting because it implies its birthplace had different temperature and chemistry than our inner solar system. Here's the counterintuitive part. Even though it acts like a comet, we can't just assume it's the same as comets we grew up with. Interstellar space is a filter. Ejected objects can be crusted over, weathered by cosmic rays or depleted of the usual surface ices. So the timing of the coma turning on and the exact gases we see give clues to its formation environment and time spent drifting between stars. That's why scientists pounced early, scheduling big telescopes to grab spectra before it swung behind the sun. Why does 3I matter beyond bragging rights? Each interstellar visitor is a random sample from another planetary system. With 3, we can start to compare. Oumuamua looked odd and small, with a non-gravitational acceleration that sparked debate. Borisov looked more like a standard comet, lots of gas and dust, textbook coma and tail. 3I Atlas lands somewhere between, clearly cometary but chemically strange. That diversity tells us interstellar space is stocked with a range of material, icy, rocky, devolatilized, maybe even processed by different stars, radiation fields. Let's pause on the why the angle and path rule out a bound comet question, because it's a common confusion. Couldn't a long-period comet from our own Oumuamua cloud come in on a very stretched ellipse that looks open? Not if you have good measurements. The data let you compute eccentricity. If it's statistically above 1, it's not bound. Plus, the inbound velocity at large distances, its so-called V-infinity, doesn't match objects falling from rest in the outer solar system. 3I Atlas has that interstellar V-infinity. That's the giveaway. Everything we've covered so far is the what of 3I Atlas, a small, active, hyperbolic visitor discovered by a sky survey, with spectroscopy hinting at carbon-rich volatiles and a coma bright enough to study. The big telescopes, Hubble, JWST, ground-based giants, join the chase because they can split the light to see which molecules are there and how the activity changes with distance from the sun. If you catch it early, you can see ices that sublimate at very low temperatures. Catch it later, and you might only see water-driven outgassing closer in. Here's what most people miss about those early uncertainties. Small errors in positions can ripple into big differences in orbit classification when you're only a few nights in. That's why astronomers obsess over residuals, independent confirmations, and cross-checks. With 3I Atlas, the community moved fast, and the interstellar verdict held. That's the what. Here's why this one makes astronomers uneasy. Compared to the comets we know, some of the chemistry and brightness trends don't line up cleanly. There's talk of nickel signatures without the usual iron lines, cyanide and carbon compounds behaving in unusual ratios, and possibly early activity that seems too strong for its distance. Are those real anomalies or measurement artifacts? We'll dig into that next, because the answer shapes whether 3I Atlas is just a quirky comet, or something that forces us to rethink what interstellar visitors can be. The weird stuff, what makes 3I Atlas different? Here's what most people miss. Weird in comets isn't one thing, it's a stack of small mismatches that add up. With 3I Atlas, the first mismatch is brightness versus expected activity. Okay, so basically, at distances where water ice should still be asleep, 3I Atlas turned on more than a typical long-period comet would. That hints at supervolatiles, CO2 or CO, driving gas flow early. When carbon dioxide vents, it can loft dust efficiently, making a coma that looks overpowered for the sunlight it's getting. In other words, the light we see is outsized for the heat budget if water is the only player. But here's the weird part. The color and gas ratios don't cleanly match our usual solar system playbook. Think of it like this. Most comets brighten in a way that roughly tracks the square of how sunlight increases as they approach. 3I Atlas's curve shows spurts that suggest changes in surface layers, crust fractures, fresh patches exposed, sudden access to volatile pockets. That's not unheard of, but pair it with spectral hints and eyebrows go up. Telescopes picking apart the light reported strong carbon dioxide, trace carbon monoxide, modest water, and signs of carbonyl sulfide. On top of that, there are cyanide bands, CN, that can make the comet look green as sunlight pumps those molecules. None of that alone is wild. It's the relative strengths and timing that feel off. The nickel reports are where debate heats up. Observers using high-resolution spectrographs flagged atomic nickel in the tail region, while iron lines looked quiet or absent. In solar system comets, nickel and iron tend to travel together in roughly similar proportions when liberated from dust grains. So nickel alone is a head tilter. One proposed fix is chemistry. If nickel is bound in a volatile complex, nickel tetracarbonyl, it can vaporize and photo-dissociate into free nickel and Co under UV light at lower temperatures than iron-bearing compounds. In other words, the nickel might get a chemical express lane out of the dust while iron stays locked up. That's a plausible natural path, but it's not routine, and it depends on how carbon-rich and cold the formation environment was. Now, did astronomers actually see non-gravitational acceleration? The same kind of tiny push that ignited the Oumuamua debate? The honest answer today is, it's being chased, constrained, and argued over. That's why it's tricky. To measure a tiny rocket-like thrust from outgassing, you have to subtract everything gravity explains with painful precision. That means exquisite astrometry over many nights, independent teams, and models that account for how the activity changes with sunlight. Early claims often wobble as more data arrive. For 3I Atlas, there's chatter about small residuals that might hint at a push, but the confidence isn't there yet. And critically, any claimed acceleration has to line up with observed gas output. Otherwise, you're implying thrust without fuel. Comet timing adds nuance. If activity came too early, supervolatiles fit. If activity seems too late, that could mean a devolatilized crust where only deeper pockets vent after cracks form. With 3I Atlas, the story leans early and carbon-driven, which matches the CO2-rich spectra. But brightness can be biased by geometry. Here's what most people miss. Viewing angle matters. If we're seeing a dust jet more face-on, it looks brighter. If large, reflective grains dominate, the comet can appear luminous without much gas. A dip in gas lines coupled with strong dust scattering can mimic power. On the flip side, fragmentation, small chunks breaking off, can boost cross-section abruptly and fade later as the swarm disperses. Each of these degeneracies can fake, amplify, or hide signals in the photometry and spectra. Rotation complicates everything. A tumbling nucleus can expose different vents to sunlight, causing flicker in the light curve and asymmetries in the tail. If you catch the comet during a favorable spin phase, you'll think it's unusually active. Observe half a rotation later and it chills. Teams try to fit periodicities to disentangle spin from secular brightening, but it takes time and clean, consistent data. Let's drill the chemistry a bit more. CO2 dominant activity far out suggests formation in a colder region than where typical water-rich comets originate, or at least preservation of those volatiles over long interstellar travel. Carbonyl sulfide is interesting because it ties to sulfur chemistry in cold environments. Cyanide production scaling can go nonlinearly with distance if grain fragmentation feeds radicals efficiently. So the green phase isn't magic. It's sunlight pumping CN and C2 after parent molecules break apart. Still, if CN ramps up faster than models predict, you either have an unusual reservoir or a pathway, like UV-processed crust, that liberates CN precursors more efficiently than we're used to. So why do some people leap to technology? Enter the intuition trap. Nickel without iron looks engineered like a refined alloy. An early, carbon-fueled outgassing looks like propellant. A stable, possibly thin coma could be read as a controlled exhaust. But that's reading intent into chemistry. The cleaner approach is to ask, is there a robust natural mechanism that fits all the data with fewer assumptions? Nickel tetracarbonyl is one candidate. Another is grain size sorting. Nanograins containing nickel compounds heat and release faster than iron-bearing grains. Add in radiolysis during interstellar travel that changes surface chemistry. Cosmic rays can rearrange bonds, making exotic carbon metal species more prevalent at the crust. And you've got a path from mundane physics to odd spectra. Here's the counterintuitive part. Detecting no iron is much harder than detecting some nickel. Absence is fragile evidence. Iron lines might be faint, blended, or swamped by noise. Slight calibration offsets can bury weak features. Spectra taken under different conditions, air mass, moonlight, instrument temperature, can push marginal lines below detection. That's why independent confirmations matter. If multiple high-resolution instruments at different observatories report the same nickel feature and similarly tight constraints on iron, confidence grows. Until then, treat nickel alone as a strong hint, not a verdict. What about the tail and coma shape? An antisolar dust tail is normal. Radiation pressure pushes dust away from the sun. A gas tail tends to align with the solar wind. If 3I Atlas shows a narrow, persistent feature pointing wrong, that might hint at directed jets or rotation-locked vents. But there's an innocent explanation. A dominant active region plus rotation can create a corkscrew-like dust stream that, when projected on the sky, looks like a steady filament. You need time-resolved imaging to tell. Putting it together, 3I Atlas looks different because several sliders are pushed away from the middle. Early, Co2-driven activity, unusual nickel signatures with weak or absent iron, cyanide and carbon compounds that light up the coma more than expected, and brightness behavior that hints at geometry, rotation, or fragmentation layered on top. None of these individually screams impossible, but together they earn the "this is odd" label. Here, what would ease nerves. A clean suite of spectra across wavelengths, optical for metal lines, near-infrared for volatiles, mid-infrared for thermal properties, taken repeatedly as distance changes. Pair that with precise astrometry to test for any non-gravitational acceleration and light curves to nail rotation. If the nickel story holds and iron continues to hide, we'll need a polished natural pathway that predicts that ratio and its evolution. If an acceleration shows up without matching gas, then the conversation changes. If it's weird, why jump to technology? Enter Avi Loeb. The Avi Loeb hypothesis, what he's actually claiming. Here's what most people miss about Avi Loeb. He's not claiming aliens did it as a default. He's saying, treat technology as a live hypothesis when the data resist natural explanations, and then ask for tests that could falsify it. That framing is why he became the lightning rod for Oumuamua in 2017. He argued its odd acceleration and reflectivity fit a thin, light sail-like object pushed by sunlight. Then he doubled down with IM-1. A 2014 meteor, he says, showed unusual strength and left tiny metal spheres he interprets as possibly technological. You don't have to agree to see the pattern. Flag anomalies, propose an engineered alternative, and push for decisive measurements. Okay, so basically, the core claim he'd make for 3I Atlas goes like this. If you stack early Co2-driven activity, unusual CN behavior, and a reported nickel signal without comparable iron, plus any hint of non-gravitational acceleration that isn't matched by observed outgassing, you've crossed into artificial is on the table. In his words, anomalous is not proof, but it's a reason to treat an artificial origin as a serious option, not a taboo. He wants astronomy to treat technosignatures the way we treat biosignatures. Specify what would count, then go look. Here's how he builds his checklist. Shape and reflectivity first. With Oumuamua, he argued that the light curve could fit an extreme aspect ratio and unusually bright surface. For 3I Atlas, a coma hides the body, so shape is harder, but he still points to photometric behavior, flares, plateaus, rotational modulation, as potential hints of engineered geometry or panels. Reflectivity matters because thin films or metallic coatings respond strongly to sunlight pressure. A higher than expected radiation pressure signature would be a red flag. Acceleration is second. The simple version is, if the trajectory deviates from gravity in a way that scales like sunlight pressure and you don't detect enough gas to explain thrust, you've got a problem. For Oumuamua, that's exactly the wedge he used, small but consistent acceleration with no clear outgassing lines. For 3I Atlas, he'd argue the bar is even clearer. Since it's actively outgassing, the measured push should match the gas production rate and direction. If the math says the force is too large or misaligned, he reads that as a Techno-Signature hint. Composition is third. The counterintuitive part is his interest in the nickel versus iron story. In natural comets, iron and nickel tend to travel together when dust heats up. Reports of nickel lines with weak or absent iron act in his framing like a metallurgical fingerprint, closer to refined alloy behavior than primitive dust. He's not saying it's stainless steel. He's saying the ratio and volatility pathway could look engineered if iron stubbornly refuses to show while nickel escapes easily. He'll cite exotic compounds, like nickel tetracarbonyl, as a natural out, then ask whether the observed strengths and distances actually fit those models, or whether you need a different explanation entirely. Everything clicked for him with the thin film idea. A light sail or vapor-deposited foil responds to radiation pressure with atom-mass ratios much higher than rocks. The physics is simple. Sunlight delivers momentum. A thin reflecting sheet gets a measurable push. The ask is demanding, though. To explain kilometer-scale accelerations with a film, you need thickness on the order of fractions of a millimeter or less and low density, plus durability against micrometeoroids and thermal cycling. He's comfortable positing advanced materials because the hypothesis is technological, but he still ties it to measurable outcomes, a specific acceleration law, a phase function in the light curve, or polarization signatures consistent with specular reflection. Here's what most people miss about how he generalizes from Oumuamua to 3I Atlas. He doesn't need them to be the same object type. He needs them to belong to a family of manufactured debris, like sails, panels, or fragments, that different civilizations could eject, discard, or lose. In that view, diversity isn't a bug, it's expected. One fragment could be inert and shiny. Another could be coated with frost and masquerade as a comet. A third could even carry volatiles for stabilization and then show a hybrid signature. The unifying theme is systematic, directionally consistent anomalies, radiation pressure-like acceleration without enough gas, reflectance and polarization pointing to thin, smooth surfaces, odd metallurgical ratios. So what does he actually want astronomers to do? 3 things. First, schedule dense, multi-wavelength observations, optical spectra for metal lines, near-IR for volatiles, mid-IR for thermal emission to lock composition and heat flow. Second, push for the cleanest astrometry possible from independent observatories to constrain any non-gravitational acceleration down to tiny residuals. Third, measure polarization and time-resolved light curves. Engineered surfaces polarize and flash differently than fluffy dust. If those data line up with natural models, great. Techno-Signature hypothesis rejected. If they don't, escalate. The counterargument he expects is straightforward. Extraordinary claims demand extraordinary evidence. He answers with a shift in burden. Extraordinary anomalies demand extraordinary tests. In other words, don't accept an ad hoc natural patch just because artificial feels uncomfortable. Specify the natural mechanism, show it predicts the numbers, and make a prediction for the next observation. If it fails, keep artificial on the table. Now where does this go off the rails? Sometimes in how fast he moves from anomaly to narrative. A nickel without iron hint could be real, or it could be a calibration quirk, line blending, or selection effects in dust release. A small acceleration could be there, or it could evaporate with better data. He knows that. His goal is to force the issue while the object is still observable, because missing the window means losing the only chance to decide. In other words, Loeb's actual claim for 3I Atlas is it's aliens. It's treat technology as a tractable hypothesis, write down the critical tests and do them now. Okay, so what does mainstream astronomy say back? Mainstream view, natural origins on the table. Here, what mainstream astronomers say, and it's more grounded than dramatic. Interstellar objects aren't rare because nature struggles to make them. They're rare because we struggle to detect them. Planet formation is messy. Young systems build planets by smashing together billions of icy and rocky pieces. Giant planets sling far more of those pieces out than they accrete. Over billions of years, every stellar system becomes a factory that ejects debris into interstellar space. So a hyperbolic comet like 3I Atlas isn't a surprise. It's the expected background finally visible with modern surveys. Okay, so basically, start with the ejection pipeline. When a giant planet perturbs a small body at the right moment, a gravitational assist kicks it to escape speed. Repeat that over millions of orbits, and your planetary system seeds the galaxy with leftovers. Most of these bodies are icy, formed beyond the snow lines where water, CO2, and CO condensed. If that's your default, then a comet with early, CO2-driven activity fits the playbook. The difference with 3I Atlas is not, it exists, but its chemistry and timing sit at the edge of our experience. Edge cases happen when you sample a new population. Natural mechanisms can also make anomalies that look exotic at first pass. Outgassing jets aren't uniform thrusters. They depend on illumination, crack geometry, and rotation. A single vent can dominate the force budget, pushing the nucleus in a way that deviates from a smooth sublimation model. If your photometry catches the comet during a jeton phase, you'll infer a larger non-gravitational acceleration than the time-averaged force. That's a known effect in solar system comets. It doesn't require exotic physics, just patchy activity, seasonal effects, and spin-axis geometry you haven't solved yet. Devolatilized crusts are another mainstream lever. After many perihelion passes, or after long exposure to cosmic rays in interstellar space, surface layers can become crusty, insulating the ices beneath. Activity then turns on where fractures open, or where dark spots absorb heat more efficiently. That can shift the gas mix toward molecules that escape through microfractures, emphasizing CO2 or CO if those gases find easier pathways than water. Fragmentation further muddies signals. Break off a swarm of meter-scale pieces, and the total dust cross-section spikes, while gas lines may lag or diffuse, changing apparent correlations between brightness and sublimation. Spectral oddities are notoriously fragile. Measuring faint lines against a bright continuum in a moving, extended source is hard. Instrumental response, sky background, and line blending can bias results toward detections that later shrink. That's why mainstream teams harp on independent instruments and repeatability. If one spectrograph flags nickel with no iron, the community asks other facilities to check at different resolutions and wavelengths. A consistent nickel detection across platforms is compelling. The absence of iron is trickier. Non-detections depend on sensitivity limits, atmospheric conditions, and modeling assumptions. Mainstream view, treat nickel present, iron absent as a working hypothesis until cross-checked. Population statistics help too. With only 3 interstellar visitors, selection effects dominate. 1I/Oumuamua looked rocky or devolatilized. 2I/Borisov looked like a textbook comet. 3I Atlas is CO2 rich with quirks. That diversity isn't a crisis. It matches expectations from planet formation theory. Different systems have different temperature profiles, snowline locations, and elemental abundances. Bodies ejected early in a system's life might be richer in supervolatiles. Bodies weathered longer may show processed crusts and unusual release pathways. Mainstream interpretation. The differences teach us about formation zones and histories, not about intent. Why is weird not enough to cross into artificial? Because natural parameter space is huge and undersampled. Before you claim engineering, you ask whether reasonable, testable natural models can explain the numbers with minimal special pleading. For 3I Atlas, plausible natural paths include carbon-rich birth environments that favor CO2, interstellar processing that enhances volatile metal-carbon complexes, grain-size distributions that change line strengths, and anisotropic jets that skew dynamical fits. If those mechanisms quantitatively match observations, line ratios, thermal emission, and any measured acceleration, then you've explained the anomaly without invoking technology. The standard of evidence in mainstream astronomy is also specific: repeatability, independent confirmation, and predictive power. Repeatability means another instrument can see the same feature under different conditions. Independence means separate teams with different reduction pipelines get consistent results. Predictive power means your model says, at this distance, the CN band will double while CO2 plateaus, and then that happens. A model that only explains after the fact is weak. A model that predicts a turn in the light curve or a change in polarization and nails it wins. Here's what most people miss about tiny accelerations. A claimed non-gravitational push must beat systematics, catalog star positions, atmospheric refraction, tracking errors, and coma-related centroid shifts. If your target's center moves because the coma brightens asymmetrically, your astrometry can fake a thrust. Mainstream teams correct for this with careful image modeling, but it's a reminder that small claims need big discipline. That's why most early acceleration hints fade or shrink with better data. Another mainstream anchor is thermal physics. If 3I Atlas's mid-infrared emission matches a porous, dusty coma heated by sunlight, with temperatures and grain sizes consistent with lab measurements, that favors a natural interpretation. If the thermal data require a high-albedo, thin, specular surface at odds with fluffy dust, then the conversation changes. Until then, a natural coma with CO2-driven sublimation is the default. What about the nickel puzzle specifically? Mainstream chemistry offers a pathway. Nickel bound in volatile carbonyls can be released and photo-dissociated more readily than iron-bearing species, especially in a carbon-rich coma with UV exposure. If multiple spectra confirm the nickel line strengths and iron limits, models can tune the parent abundances and photochemistry to match. The prediction would be simple and testable. As solar UV flux rises with proximity, the nickel line should strengthen following a specific curve tied to photo-dissociation rates, while iron lags until higher temperatures or different fragmentation liberate it. If observations follow that curve, the natural model gains weight. Population expectations also argue against exotic conclusions. Models predict that most ejected interstellar bodies are icy, with a tail of rocky fragments. Seeing an active comet as the third entry tracks with those priors. Even the cyanide-rich, green glow phase aligns with known comet behavior under strong UV pumping. The surprise is magnitude, not mechanism. The mainstream stance is, unusual composition ratios are data about origin environments, not evidence of design. Finally, there's a pragmatic point. Artificial origin claims must clear a higher bar because they posit intent and engineering. That bar includes signatures like controlled course changes, waste heat inconsistent with passive heating, narrowband radio or optical beacons, or polarization patterns matching smooth manufactured films. Absent those, the null hypothesis, natural comet, stands. Not because of bias, but because simpler models with fewer assumptions explain more. But there's one observation that keeps the debate alive. Remember that detail. If a robust, repeatable non-gravitational acceleration appears that's too large or misaligned for the measured gas output. Then even mainstream voices admit we need either a new natural mechanism or a serious conversation about alternatives. That's the pivot point we'll tackle next. The one detail that changes the debate. Here's the detail: a possible non-gravitational acceleration without clear gas signatures to power it. If that holds up big if, it tilts the whole conversation because it echoes the Oumuamua fight. Back then, a tiny but consistent extra push showed up in the trajectory fits, and the usual culprits, water jets, outgassing, didn't show strong spectral lines. The mismatch between force and fuel became the battlefield. With 3I Atlas, seeing a similar mismatch would matter even more because this object is actively venting. If the push is too large or pointed the wrong way relative to the gas flow, that's a red flag. Why is this a red flag? Okay, so basically, comets are rocket engines with messy plumbing. Sunlight heats the surface, volatile ices sublimate, gas vents through cracks, and you get thrust in the opposite direction. The push should roughly correlate with the gas production rate, and its direction should line up with the geometry of the active regions averaged over a rotation. If the measured acceleration exceeds what the observed outgassing can provide, you either missed some invisible propellant, or you measured the push wrong. If it points in a direction that gas can't reasonably produce, then your model for the nucleus shape, spin, or jet distribution is off, or something else is at work. Everything clicked when I realized this isn't just magnitude, it's alignment. A jet on the sunlit hemisphere tends to push roughly anti-solar on average. Over a rotation, the vector can wobble, but it won't consistently point sunward, and it won't ignore the light curve. If astrometry suggests a steady acceleration scaling with solar radiation pressure, falling off like 1 over distance squared, and you don't see enough dust or gas to explain it, that's exactly the Oumuamua pattern that raised eyebrows. For 3I Atlas, the presence of a coma gives us more levers. We can estimate gas from spectral lines and dust from scattered light, then compare the implied momentum flux to the trajectory residuals. Now, alternative explanations deserve first shot. Start with sublimating supervolatiles. CO and CO2 can drive strong activity far from the sun, and if the nucleus has a patchy crust, a single dominant vent could produce thrust outsized for its brightness. The dust recoil idea adds another layer. Large grains lofted preferentially in one direction can carry momentum efficiently without leaving strong gas signatures in some bands, especially if grain size skews the reflectance. Shape-induced forces can also trick you. A lumpy, rotating nucleus can shift the light centroid of the coma as different facets brighten, and if you measure positions off the brightness peak instead of the true center of mass, you can bake an artificial acceleration into your astrometry. Data quality is the trapdoor under this debate. Tiny biases mimic thrust. Here are the usual suspects. First, centroid shifts from asymmetric comae. If one side of the coma brightens due to a jet, the measured center moves even if the nucleus doesn't. Second, reference star catalogs. Residual proper motion errors or color terms in the astrometric solution slide positions just enough to fake curvature. Third, tracking smearing. Long exposures on a moving target can elongate the source, and reduction pipelines that assume point sources can bias the fit. Fourth, timing and clock sync. Millisecond-level errors can matter when you're stacking many nights to pull out a tiny acceleration. Each one is small. Together, they can impersonate a weak non-gravitational force. Here's the weird part. Absence of evidence cuts both ways. If you claim no gas, you have to define the detection limits and the specific lines you looked for. CO2 is tricky in the optical. You often infer it from near-infrared or from proxies. Iron lines can hide in blends. Weak emissions drown in sky noise. So a fair test compares apples to apples. The momentum you need from thrust versus the momentum you can supply from measured gas production, with error bars that capture all the uncertainties. If those bands don't overlap, you've got a problem the natural models must solve. What would a decisive test look like? 3 pieces. First, high-resolution multi-epoch spectra that go after parent and daughter species, Co2, Co, H2O, CN, C2, plus metal lines like Ni and Phi, over a range of distances. That pins down gas production and its evolution. Second, a thermal model fit anchored by mid-infrared observations to constrain dust grain sizes, temperatures, and albedo. That tells you how much solar energy is available and where it goes. Third, ultra-precise astrometry from independent observatories, corrected for coma asymmetry using image modeling, to extract any residual acceleration and its direction. If the inferred force matches the gas within uncertainties and points where the active regions are, it's natural. If it doesn't, you escalate. There's a micro-story that shows how these tests save face. Years ago, a weird asteroid showed a steady acceleration and odd reflectivity. It screamed exotic until someone checked archival images and realized it was a spent rocket upper stage. Thin-walled, low density, high area to mass, pushed by sunlight. The giveaway was polarization and a telltale spectral slope. The lesson is simple. When data sets multiply, optical, IR, polarization, radar if you're lucky, the space for misinterpretation shrinks. For 3I Atlas, polarization could separate fluffy dust from specular surfaces. Thermal color could flag thin films versus porous grains. Okay, but here's what most people miss about shape-induced forces. Radiation pressure on dust in the coma, and on any large, low-mass debris can create a net push that looks like a nucleus acceleration if your model ties the center to brightness. You fix that by modeling the coma's surface brightness and subtracting its contribution before fitting positions. If the acceleration survives that cleaning and still follows a 1/r² law too strong for dust alone, that's compelling. One more alternative pathway: episodic outbursts. Short, sharp jets can kick the nucleus subtly and then die down, leaving a blended signal that over weeks mimics a steady acceleration in simple fits. Time-resolved photometry helps here. If brightness spikes line up with the inferred acceleration vector changing, you're probably seeing jet physics, not exotic propulsion. If the vector sits steady while activity swings, that's harder to square naturally. So where does this leave us? The one detail that changes the debate is a clean, repeatable non-gravitational acceleration that's quantitatively inconsistent with measured outgassing and dust recoil, especially if its distance dependence matches radiation pressure on a high area-to-mass object. That would force either a new natural mechanism, some combination of photochemical nickel-bearing volatiles, grain sorting, and jet geometry we haven't modeled, or a serious look at artificial surfaces. Before calling it alien, though, we need those decisive tests, spectra that lock the fuel, thermal models that pin the budget, and astrometry that nails the push. Only then do we earn the next step in the argument: how interstellar visitors are made and flung at us. Okay, so basically, interstellar visitors are the leftovers of planet building that got kicked too hard and never came back. Start at the beginning. A young star forms from a collapsing cloud, surrounded by a swirling disk of gas and dust. In that disk, tiny grains collide, stick, and grow into pebbles, then boulders, then kilometer-scale planetesimals. Most don't become planets. They become the raw inventory, icy and rocky bodies, parked in different temperature zones called snow lines, where specific ices can condense. Think of snow lines as chemical borders. Closest to the star, it's too hot for water to freeze. Farther out, water ice is stable. Beyond that, carbon monoxide and carbon dioxide can solidify. Bodies born beyond the Co2 and Co snow lines lock in supervolatile ices that sublimate at lower temperatures. That's crucial for 3I Atlas. Co2-driven activity far from the Sun implies a cold formation environment where those ices were abundant and preserved. Here's what most people miss. The same giant planets that shepherd planets into place also act like cosmic bouncers. When a planetesimal wanders too close to a giant, A gravitational slingshot can pump its energy up or down. A few close passes, timed right, and the small body's orbit crosses the system's escape velocity. It's not rare on long timescales. It's inevitable. Simulations show that a large fraction of the original disk mass is ejected over tens to hundreds of millions of years, especially in systems with massive, migrating giants. The counterintuitive part is that ejection beats accretion. Giant planets are efficient at scattering. They fling far more objects away than they absorb. In compact systems, planet-planet resonances stir the disk, and mutual nudges deliver planetesimals into slingshot lanes. Each encounter changes speed and direction. After a handful of kicks, the little body is on a hyperbolic exit, preserving whatever ices and minerals it carried from its birth zone. That's how you stock the galaxy with debris, the background ocean that occasionally sends a wave through our shore. Now zoom out to the stellar nursery. Stars don't form alone, they're born in clusters. In those crowded cradles, neighboring stars pass relatively close in the first few million years. Those flybys torque outer disks, stripping and stirring Kuiper belt analogs. A well-timed encounter can dislodge thousands of comets, boosting the ejection rate beyond what planets alone would do. Add in the cluster's tidal field and occasional supernova shocks, and you've got extra ways to shake loose the edges. The result is a spray of icy bodies into interstellar space, with velocities set by the host star's motion, plus the kicks from encounters and planets. Space is not a freezer, it's a slow oven. Once ejected, a body spends millions to billions of years cruising between stars. Cosmic rays and UV photons process the surface, breaking chemical bonds, darkening the crust, and welding a thin, devolatilized rind. That rind matters. It can trap deeper ices, delay activity until closer to a star, and alter which molecules escape first when heating begins. Over long times, volatiles near the surface are depleted, while exotic species, like carbonyls and complex organics, can concentrate or form via radiolysis. That's one way to set up weird chemistry, not by alien craftwork but by interstellar weathering. Okay, so what would nickel and cyanide tell us about birthplaces? Nickel is a refractory metal, typically bound in dust grains with iron. If nickel shows up before iron, you may be seeing a volatile carrier liberating it more easily, consistent with carbon-rich environments where nickel tetracarbonyl can form under low temperatures and co-rich conditions. Cyanide, seen as CN in Comet, traces the breakdown of parent nitriles and organics. High CN at long distances implies a reservoir of nitrogen-bearing compounds that crack under UV. Put together, a body born beyond the CO2 snow lines in a carbon-rich zone, then processed in interstellar space, could show early CO2 activity, strong CN, and unusual metal release pathways. Everything clicked when I realized ejection timing imprints chemistry. Early ejection, while the disk still has gas, can strip mantles, alter spins, and even coat surfaces with nebular residues. Late ejection preserves more pristine layering but gives space weathering more time to work. Systems with hot Jupiters migrating inward can toss bodies outward in chaotic episodes, sampling a wide range of formation radii. Systems with multiple Neptunes in the outer disk can steady drip eject material for eons. Diversity at the source means diversity in visitors. That's why Oumuamua, Borisov, and 3I Atlas don't match each other neatly. Here's the weird part. The distribution of spin states also comes from birth and ejection. Close encounters can impart tumbling, and YORP-like torques, tiny forces from uneven sunlight absorption and re-radiation, can spin bodies up or down over long times. Tumbling changes how heat and radiation interact with the surface, which changes venting patterns during the next stellar flyby. The same object could present a different personality each time it wakes up, depending on which face cracks first. What about size? Ejection favors smaller bodies because they're more easily perturbed and require less energy to launch. But too small, and they sputter away or are ground down by micrometeoroids over gig-years. That sets a sweet spot for interstellar longevity. Tens of meters to a few kilometers, porous, dark, with enough cohesion to survive but light enough to be kicked. Comets that size can carry dust and ices shielded by a crust, ready to vent when sunlight returns. That's exactly the scale where surveys like Atlas and larger telescopes can detect them as they brighten. Let's talk selection bias, because it shapes what made means in our sample. We're more likely to spot active bodies than inert rocks of the same size because Comets amplify brightness. We're more likely to see objects approaching from the night side of Earth and at angles where background star density is manageable. And we're more likely to detect those with higher albedos or larger dust production. So the first few interstellar objects we catalog skew comet-like and bold. That doesn't mean rocky fragments aren't out there. It means we haven't built the all-sky, all-time sensitivity to catch the quieter ones consistently yet. Chemical fingerprints survive the trip in layered form. The outer centimeters bear the marks of cosmic rays, complex organics, cross-linked carbon networks, perhaps carbonyl complexes that can release metals under UV. Beneath that, preserved ice mixes, water, Co2, Co-minor species like carbonyl sulfide, sit in pores. When the object warms, sublimation begins in pockets, gas percolates through cracks, entrains dust, and erupts as jets. The initial burst can be Co2 dominant, followed by water closer in. If nickel-bearing carbonyls exist in dust grains, they can release nickel earlier than iron-bearing minerals, explaining timing offsets without invoking anything engineered. Here's what most people miss about albedo and color changes. Interstellar weathering tends to darken and redden surfaces, but fresh fractures expose brighter, icier material. That creates time-variable reflectance that can confuse shape and size estimates from light curves. It also modulates how radiation pressure and thermal forces act, tweaking the tiny, cumulative effects that matter for precision trajectory fits. So how do you actually fling an object like 3I Atlas at us? Combine three ingredients: a planet-perturbed orbit that reaches escape, a cluster environment that shakes outer reservoirs, and enough time for the object to drift into our path. The sun carries us through the galaxy at tens of kilometers per second. Local interstellar debris shares the ride with different random velocities. Every so often, geometry lines up. The visitor drops into our potential well, accelerates, brightens as it warms, and gives us a fleeting chance to read its history. What this actually means is we should expect variety. 1I looked devolatilized and odd, 2I looked comet classic, 3I is cometary but chemically skewed toward carbon. None of that is a contradiction. It's the signature of a galaxy-sized experiment in planet formation and ejection. The job now is to decode the mix, map the chemistry to birth zones, map activity timing to crust properties, and map dynamics to ejection pathways. Now, can we actually tell natural from artificial with current tools? We can, but only if we know exactly what to test for and how to read the signals. The natural vs. artificial checklist. Here's why this checklist matters. If we confuse exotic geology for technology, we waste telescope time chasing ghosts. If we miss real technosignatures, we miss the discovery of our lifetime. The point isn't to sensationalize. It's to separate unusual but natural from unlikely without intent, using signals we can actually measure. Okay, so basically, we'll define what to look for, why it matters, and how to test it fast. Start with anomalous acceleration. Why it matters. Motion is the cleanest physics we've got. Gravity is predictable. Deviations are either thrust from outgassing, radiation pressure on high area-to-mass material, or analysis artifacts. The aha is that each cause leaves a different fingerprint. What to look for? A force that scales like sunlight intensity, roughly 1 over the square of distance, aligned anti-solar if it's radiation pressure, or tied to active regions if it's jet thrust. If you can't account for it with measured gas and dust, the residual is suspicious. How to test? Independent astrometry with coma centroid correction, fit both gravity-only and non-gravitational models, and compare against gas production from spectra. If the acceleration law fits radiation pressure and the area to mass implied is too high for a rubble body, flag it. Next, engineered symmetry and shape. Why it matters. Nature rarely makes large, flat, specular sheets that maintain a stable attitude without significant tumbling. Humans do. What to look for? Light curves with sharp specular glints, unusually deep amplitude consistent across wavelengths, and period stability inconsistent with chaotic tumbling. Also, geometric albedo or polarization that suggests smooth surfaces rather than fluffy aggregates. How to test? High-cadence photometry over multiple rotations, multi-band phase curves, and linear circular polarization measurements. If the polarization angle tracks like a mirror, not like dust, that's a tell. Third, non-natural spectra. Why it matters. Molecules and metals tell origin stories. Natural comets show families of volatiles and fragment species. Engineered materials can show narrow emission from coatings, dopants, or processing residues, or an absence of expected lines. What to look for? Persistent metal ratios that defy known condensation sequences or carbonyl pathways across distances, narrow lines at unusual wavelengths, reflectance edges like manufactured films. How to test? Cross-check spectra from optical through mid-infrared, map line ratios against heliocentric distance, and verify against lab databases. If a line repeats across instruments but lacks a plausible parent species, push it up the list. Fourth, power and propulsion signatures. Why it matters. Machines waste energy. Even efficient systems leak heat or produce characteristic emissions. What to look for? Mid-infrared excess inconsistent with passive heating and dust, narrowband optical or radio beacons, forbidden lines or ionization states implying sustained power. How to test? Mid-IR photometry to fit thermal models, radio searches across standard beacon bands, and high-resolution spectroscopy for unusual ion lines. If the thermal curve demands internal power at large distances, that's not a comet problem. It's an engineering problem. Fifth, trajectory intent. Why it matters. Comets don't aim. They arrive on passive hyperbolas set by initial conditions. What to look for? Course changes not explainable by jets, especially vector flips inconsistent with rotation average thrust, station keeping near resonance points, velocity changes that don't map to outgassing phases. How to test? Stack astrometry over weeks, correlate any vector shift with light curve or outburst timing, and simulate plausible jet distributions. If the residuals imply an energy budget and directionality that jets can't match, you've left natural dynamics. Now, how to test any of this with the tools we have. Multi-wavelength is non-negotiable. Optical grabs metal lines and radicals. Near-infrared spies on Co2, Co, H2O. Mid-infrared pins temperatures and grain sizes. Polarization separates shiny from fluffy. If geometry cooperates and the object comes close enough, radar is a golden hammer. It measures size, shape hints, and surface roughness directly. For most interstellar visitors, radar's a long shot, but polarization and light curves fill a lot of the gap. We also need discipline with statistics. Correlation isn't causation. A brightening spike and a trajectory kink might coincide by chance unless the phase behavior and timing match a physical model. Build falsifiable predictions. If a jet drives the push, the acceleration vector should precess with the rotation period. If radiation pressure rules, the magnitude should scale with 1 over r squared, and the implied area to mass should be stable. If those predictions fail across multiple nights, mark it down. Power and propulsion deserve a sanity check. Waste heat scales with power. A square meter sail pushed by sunlight doesn't need internal power, so no excess heat. A powered thruster does. Look for mid-IR emission that stays high when sunlight falls, or a color temperature too warm for distance and albedo. For line emissions, engineered systems might leak narrow, coherent signals. Most comets show broad, thermalized lines tied to gas temperatures. A narrow, persistent, unblended line at a fixed frequency across nights. That's a jump to the front of the queue event. Trajectory intent overlaps with context. A passive hyperbola is not suspicious. The giveaway would be a mid-course tweak that doesn't line up with activity. Here, the counterintuitive part. Even natural comets sometimes look intentional if you undersample rotation and jet cycles. That's why dense cadence matters. Sample sparsely, and you can mistake periodic jet thrust for a deliberate burn. Sample densely, and the wobble reveals itself. Let's drop in a micro-story that keeps everyone honest. A mystery asteroid once looked shiny, light, and slightly accelerated by sunlight. People whispered exotic. It turned out to be a spent rocket upper stage, thin-walled and high area to mass, coated in reflective paint. Polarization plus a telltale spectral slope gave it away. The lesson is not, it's always a rocket. It's when the checklist points to thin, reflective, low-density material and the kinematics agree, you might be looking at hardware, ours or someone else's. Process first, narrative second. Okay, so basically, here's the compact checklist you actually use at the telescope. Acceleration. Is there a residual after gas and dust momentum is accounted for, and does it scale like radiation pressure? Surface cues. Do light curves and polarization imply smooth, specular surfaces or fluffy dust? Spectra. Do line ratios and edges match known volatiles and minerals, or do you see persistent outliers across instruments? Thermal. Does mid-IR fit passive dust, or is there excess demanding internal power? Trajectory. Any vector changes uncoupled from activity. Nobody explains this right, but the order matters. Dynamics first, then composition, then surfaces, then heat, then intent. That sequence moves from hardest to fake physics to most narrative-friendly inference. If an object clears the first two hurdles with natural explanations, the later Techno-Signature boxes usually fall away. If it fails early, you mobilize everything. Bigger telescopes, tighter cadence, broader bands, because you might be on to something rare. Everything clicked when I realized the goal isn't to prove alien or not alien. It's to leave as little gray area as possible while the window is open. Interstellar visitors are fast, faint, and fleeting. A clean, pre-agreed checklist lets the community pivot quickly from curiosity to decision. If it's natural, we learn chemistry and formation. If it's not, we rewrite our place in the story. Now, let's run 3i Atlas through that filter. Running 3i Atlas through the filter. Okay, so basically, let's put 3i Atlas through the checklist we just built and see what survives contact with the data. Start with acceleration, because dynamics are the cleanest physics. Right now, the most honest status is constrained but not confirmed. Multiple teams have pushed gravity-only fits as far as they can, and then allowed a standard cometary non-gravitational term to float. The residuals shrink a bit, but not decisively enough to claim a persistent, radiation pressure-like push. That matters. If a sail-style acceleration were obvious, it would fall out quickly in independent orbit solutions. Instead, what we see is compatible with mild jet thrust and typical modeling noise, especially once you correct for coma asymmetry shifting the apparent centroid. Here's what most people miss. Even a real thrust signature has to line up with measured gas and dust. For 3i Atlas, spectra show strong CO2 activity, CN turning on hard, and dust plentiful enough to build a healthy coma. That's fuel. So a modest non-gravitational term is expected. The question is whether the amplitude and direction match the observed outgassing. So far, fits that allow a sunward-to-sunward component tied to illumination do a plausible job. No clean, distance-squared scaling without gas has emerged. That keeps the radiation pressure-only interpretation in the maybe-later bucket. Next filter, spectra. Do we see any lines that scream not natural? The nickel reports are the spiciest item. High-resolution observations have flagged nickel emission and, at times, weak or absent iron lines. That's unusual but not inherently artificial. In a carbon-rich coma, nickel tetracarbonyl photodissociation can release nickel earlier or more efficiently than iron-bearing species. Independent teams have started to replicate the nickel detection. Iron remains finicky, marginal in some data, buried in noise in others. The cautious read is nickel present, iron under debate, with a natural carbonyl pathway on the table. No narrow, out-of-place lines, no exotic dopants, no discrete laser-like features. Translation: interesting chemistry, yes. Engineered spectral fingerprint, not yet. Surface and rotation cues come next. Can we pull shape from the light curve, despite the blooming coma? Photometry shows variability that looks like rotation-driven modulation layered on secular brightening from activity. The amplitude isn't razor-sharp, which is what you'd expect from a dust-scattering coma washing out nucleus glints. We don't see repeating, narrow spikes consistent with specular flashes off a smooth panel. Polarization measurements, where available, lean dusty, more like fluffy aggregates than mirror-like films. That doesn't rule out small, smooth fragments buried in the coma, but it argues against a dominant, flat, engineered surface controlling the signal. Thermal behavior is a big test, so let's stress it. Mid-infrared observations fit a warm, dusty coma heated by sunlight, with color temperatures and emissivity consistent with porous grains lofted by CO2 and some water closer in. There's no persistent mid-IR excess demanding internal power at large distances where sunlight is weak. The energy budget closes. Sunlight in, sublimation and re-radiation out, with dust carrying the rest. If a powered system were hiding in there, you'd expect a telltale thermal tail, temperatures too high for the heliocentric distance, or flux that doesn't fade with the sun's inverse square law. We don't see that. Trajectory intent. Nothing suggests course corrections. The path is a clean hyperbola, with any small deviations explainable by asymmetric outgassing plus modeling uncertainties. No step-like velocity changes, no holding patterns, no resonance surfing. The vector evolves smoothly as gravity dictates, and any tiny nudges appear tied to activity phases, not independent maneuvers. That keeps intent off the table. Okay, so what does the nickel puzzle do to the verdict? It raises a well-posed question. Can we predict the nickel-to-iron signal's evolution with distance using a natural carbonyl model, and then see it play out? If upcoming spectra show nickel strengthening with UV flux in a way that tracks photodissociation rates, while iron lags and then rises closer to the sun when temperatures spike, that's a win for chemistry. If iron stays stubbornly absent across geometries and instruments, confidence in the anomaly grows. But absence is fragile. Until multiple facilities lock the iron limits down, no iron isn't a fact. It's a working claim with caveats. Let's talk degeneracies, because they're everywhere here. A bright, CO2-driven coma can overestimate activity if large, reflective grains bias photometry. Conversely, gas production rates can be underestimated if the lines used are weak, blended, or outside the instrument's sweet spot. Centroid shifts can fake accelerations. Rotation phase can fake secular changes. Fragmentation can mimic an engineered light curve by injecting short-lived cross-section. The antidote is consistency across methods. Right now, the cross-checks, astrometry from multiple sites, spectra from multiple telescopes, thermal fits from multiple bands, lean natural. Here's the counterintuitive part. 3I Atlas looks most unnatural when you isolate one subplot. Nickel without iron, weird. CN ramping faster than expected, weird. Early activity far out, weird. But the moment you stack them, a coherent natural story forms. A carbon-rich, CO2 dominant comet with interstellar weathering that favors volatile metal-carbon complexes, waking up early, lofting dust that softens light curve clues, and venting anisotropically enough to add a modest, rotation average thrust. That doesn't mean case closed. It means the burden shifts to anyone proposing technology to show a mismatch the natural model can't meet. Either a thrust law that behaves like radiation pressure without the implied area to mass, or spectral thermal features that can't come from fluffy grains and carbonyl chemistry. So what would change the verdict fast? 3 triggers. First, a robust, independent detection of a distance squared acceleration that's too large for the measured gas and dust momentum, and that keeps its direction when activity changes. Second, repeated, cross-instrument confirmation of nickel with tight iron upper limits that defy all plausible carbonyl models across heliocentric distances. Third, polarization or light curve behavior showing stable, specular flashes or mirror-like phase functions inconsistent with a dust-dominated coma. Any one of those moving past, hint, into locked would force a rethink. Until then, the provisional verdict is straightforward. 3I Atlas is best explained as a natural interstellar comet with unusual but modelable chemistry and activity. The acceleration is, at most, modest and consistent with jets. The spectra are intriguing but not alien. The thermal budget closes. The trajectory shows no intent. If future data sharpen a contradiction, force without fuel, mirrors without metals, heat without sunlight, then we revisit. And that's the real takeaway. The filter isn't a one-time pass-fail. It's a rolling test we apply as the comet evolves and the data get better. And if it stays natural, the story is still wild. Because even a normal interstellar comet is a sample return from another star's nursery, delivered to our doorstep for a few short months. Why 3I Atlas still matters, even if it's just a comet. Here's what most people miss. Just a comet from another star system is still a once-in-a-generation science gift. Okay, so basically, 3I Atlas lets us count, compare, and calibrate an entire hidden population we could only simulate before. With 1I, 2I, and now 3I, we finally have the first 3 points on the graph of interstellar object density. Every detection sharpens estimates of how many are out there per cubic astronomical unit, and how often they wander into telescope range. That number feeds into how messy planet formation is, how efficient ejection is, and even how much raw material is drifting between stars right now. Population statistics aren't just trivia, they set mission economics. If the galaxy tosses one good-sized interstellar visitor into our neighborhood every few years, agencies can justify standing interceptors. If it's once a decade, you need a different strategy, ready to launch kits and fast response protocols. 3I Atlas refines occurrence rates, size distributions, and brightness functions. And because it's clearly active, it biases our sample in a known way, which lets modelers correct for the fact that inert shards are undercounted. Everything clicked when I realized. A single detection with solid characterization constrains a big slice of parameter space, because it sits alongside 2 very different predecessors. Early solar system insight is the next payoff. Chemistry is a time machine. If 3I Atlas is too rich with strong CN, modest water early, and some sulfur chemistry, that tells us its parent disk had cold regions where supervolatiles condensed and stuck. Compare that to 2I/Borisov's more water-forward behavior and Oumuamua's devolatilized weirdness, and you start mapping where in other systems these bodies formed. The what this actually means line is simple. By reading 3I Atlas's gases and dust, we're peeking at the temperature and composition gradients in an alien protoplanetary disk, then holding that against our own history. Now the prebiotic angle, without hand-waving. CN in the coma traces nitrogen-bearing organics. Carbonyl sulfide is a known catalyst in peptide formation experiments. CO2 and CO carry carbon frameworks that can produce complex organics under UV. No, that doesn't mean life rides in on comets. It means interstellar comets can be trucks carrying prebiotic ingredients across star systems. If those ingredients are common, the starting kit for chemistry is widespread. 3I Atlas lets us test whether the inventory in another system's cold zone resembles the toolkit that likely seeded our early Earth via native comets. If the ratios line up, panspermia doesn't need microbes, just chemistry on delivery. Here's where it gets practical. Mission concepts. The real danger with interstellar visitors isn't impact, it's missing the window to learn. They're fast, they brighten quickly, and then they're gone. Agencies have learned from 1I and 2I. NASA and ESA teams have floated interceptor architectures. Small spacecraft parked in heliocentric orbits with high delta-V margins, sleeping until an alert pings them. The trick is time. From first detection to best intercept window, you might get months, not years. 3I Atlas arrives while those studies are still on the drawing board, which turns it into a live-fire drill for operations. Coordinating alerts, triaging telescope time, and rehearsing data pipelines you'll need when 4I shows up. Everything clicked when I realized 3I Atlas is also refining the playbook for ground and space telescopes. We're learning which bands to prioritize first nights. Near-IR if CO2 looks strong, optical if CN ramps, mid-IR if the thermal budget is unclear. Teams are stress-testing polarization setups, astrometry corrections for asymmetric Comet, and rapid data sharing. The lesson carries forward. When 4I appears, we won't argue about settings. We'll load the known good configuration and press go. That alone saves precious hours. And yes, amateurs matter a lot here. Interstellar comets live in brightness regimes reachable by serious backyard rigs. High-cadence light curves from citizen scientists can catch outbursts and periodicities the big observatories miss between scheduled blocks. Coordinated campaigns through networks like COBS or AAVSO feed rotation period fits, fragmentation alerts, and coma morphology changes back to the pros. For 3I Atlas, that means more eyes, more timestamps, and better coverage across longitudes and weather gaps. The how you help is simple. Calibrated photometry, time-stamped, with consistent filters and exposure norms. Dull, disciplined, powerful. Okay, but why does 3I Atlas matter, even if the nickel puzzle softens and iron creeps into the spectra later? Because it still expands the known chemical diversity of interstellar bodies. A CO2 dominant, CN-happy visitor tells us that cold formation zones and carbon-rich reservoirs are not rare. That feeds into planet formation models that predict where super-Earths and Neptunes end up, how they shepherd debris, and what kinds of outer belts other systems keep. It even nudges exoplanet habitability thinking. Disks richer in volatiles can deliver more water and organics inward if scattering is efficient. If ejection dominates, those cargoes go to interstellar space instead. 3I Atlas is a data point in that supply chain. Here's the counterintuitive part. Even a null result on Technosignatures is a win. If we run the full checklist, dynamics, spectra, polarization, thermal, and everything lands squarely in natural territory, we've validated our filters. The next time an object pings those sensors in a different way, confidence will be higher that the anomaly is real. The value isn't just the answer, it's the calibration of the questions. Finally, there's the quiet, long-tail payoff: archives. High-quality, time-resolved data on 3I Atlas will sit in public repositories for decades. Future instruments will reprocess those frames with better calibration, refit the spectra with improved line lists, and test new models against a locked history. That's how Oumuamua's debate stayed alive. Data endured. For 3I Atlas, a richer, multi-wavelength archive means the community can revisit every claim as methods improve. Today's becomes tomorrow's aha when the tools catch up. So even if 3I Atlas is just a comet, it's a comet from a different star's nursery, tightening our population counts, sharpening our chemistry maps, road testing our Techno-Signature filter, and rehearsing the intercept future. That's not a consolation prize. That's the mission. Is it dangerous? How close, how fast, what risk? Here's the straight answer. For Earth, 3I Atlas is a scientific opportunity, not a threat. Closer than you think means closer in observational terms. Good geometry for telescopes, not collision risk. Interstellar visitors zip through on clean hyperbolas, unless the orbit solution shows an impact corridor, the danger to us is effectively zero. The real risk is letting it fly by without squeezing every bit of data out of it. Okay, so basically, closest approach is the moment when the geometry is most generous. The comet is brightest, its apparent motion is manageable, and the Sun-Comet-Earth angle often improves for spectroscopy and polarization. That's why you see a flurry of observing proposals around that window. Brightness climbs as solar flux ramps up, and as the distance to Earth shrinks, then fades rapidly after perihelion as it recedes and activity drops. Closer in the title is your cue that telescopes, big and small, can get higher signal-to-noise measurements than they usually can for something so exotic. Let's talk speed. Interstellar objects come in hot. Their hyperbolic excess velocity, the leftover speed after subtracting the sun's pull, is tens of kilometers per second. Add the sun's gravity well, and they sweep through the inner system at relative speeds that can top 50-70 km/s depending on the trajectory. That sounds scary until you pair it with probability. Space is big, and impact corridors are narrow. The orbit fit for 3I Atlas is precise enough to keep Earth far off the bullseye. High speed also shortens the interaction time. By the time it gets bright enough to worry casual observers, the geometry already guarantees a miss. Kinetic energy scales with velocity squared, so yes, a hypothetical impact at interstellar speed would pack a punch. But what if isn't how risk is measured in planetary defense? Astronomers compute impact probability from the full covariance of the orbit solution. You start with many nights of astrometry, fit a trajectory, and propagate uncertainties forward. If the Earth's position never overlaps the uncertainty ellipsoid of the object's path, the probability is literally zero within the modeled window. For 3I Atlas, the path is clear. No resonant hooks, no gravitational keyholes being threaded, no late course unknowns big enough to flip the verdict. Here, that's what most people miss. Negligible isn't a vibe, it's math. The impact probability for a well-tracked hyperbolic visitor drops as 1, more data nail the orbit, and 2, the object physically passes the plane of Earth's orbit without matching Earth's timing. By the time you're watching a bright, busy coma, the impact assessment is usually done and dusted. That's why planetary defense teams can relax and hand the baton to the spectroscopy crowd. So what is the real danger? Missing the science window. Interstellar comets evolve fast. The coma chemistry at 5 astronomical units is not the same at 2, and the dust size distribution shifts as vents open and close. If we don't coordinate observations across wavelengths during the best geometry, we leave unanswered questions on the table. Was the nickel signal transient? Did iron wake up later? Did a subtle non-gravitational term appear near perihelion? Those answers require time series, not a single glamorous image. Closer than you think helps amateurs too. When geometry lines up, an object like 3I Atlas sits in reach of mid-sized backyard setups. That's not hype, it's a workflow. Here, that's how amateurs make a dent without drowning in noise. First, standardized filters. Use V or R bands for continuity with professional datasets. Second, consistent cadence. Short, repeated exposures to build high-cadence light curves that catch outbursts and periodic rotation signals. Third, calibration discipline. Bias, darks, flats, and comparison stars with well-known magnitudes. Upload through community pipelines, COBS, AAVSO, so professionals can fold your timestamps into rotation models and activity maps. Everything clicked when I realized how citizen data closes gaps. Big telescopes can't stare every night. Weather and scheduling force gaps. A global ring of small telescopes can stitch a near-continuous timeline, flagging events that trigger rapid response spectroscopy on the giants. A sudden brightening. That might be a jet turning on or a fragmentation event. A subtle periodicity. That could constrain rotation and help isolate any thrust-like residuals in the orbit fit. In other words, amateurs don't just also observe. They set the table for decisive follow-ups. What about spacecraft risk? Same logic applies. The hyperbolic path and short residence time in crowded orbital shells make conjunctions with satellites vanishingly unlikely. Dust from the coma spreads over enormous volumes at low densities. It's not a coherent stream aimed at anything. The ISS, GPS, and GEO birds are not in play. If anything, near-Sun spacecraft with coronagraphs and heliophysics missions get bonus science. They can watch dust interaction with the solar wind, sample pickup ions, and feed back into our models of comet-solar coupling. Okay, but here's the counterintuitive part. High speed actually helps observations. Fast motion across the sky gives different viewing angles night to night, which is great for deconvolving three-dimensional coma structures and jet directions. It also pushes the phase angle through a useful range, letting polarization and phase curve studies separate fluffy dust from smoother grains. The catch is you need coordination and quick reductions. Waiting weeks to share data kills the chance to act on what you find. If you want a quick checklist for the public risk question: 1. Is it on a hyperbolic orbit? Yes. 2. Does the orbit solution's uncertainty intersect Earth? Number 3. Are there gravitational keyholes that could bend it toward us later, not applicable on an exit trajectory? 4. Are we expecting a meteor stream? No, not in any concentrated hazardous sense. That's the end of the worry. Shift the question to, what can we learn before it fades? Here's the bottom line. 3I Atlas is moving fast, getting bright, and then it's gone. It's not dangerous to Earth, it's dangerous to our complacency. The only impact we should care about is the hit our understanding takes if we don't capture the spectra, light curves, polarization, and precision astrometry while the geometry is favorable. So, is Avi Loeb right, or are we chasing ghosts? The next observations will tell, but only if we make them in time. Verdicts, nuance, and what would change minds. Here's the clean verdict first. Today's best fit story is a natural interstellar comet with odd but modelable chemistry. That's not a hedge. It's where multiple lines of evidence converge. Dynamics that don't demand radiation pressure acceleration. Spectra that headline carbon dioxide and CN with intriguing nickel thermal emission that closes the solar energy budget. And a hyperbolic path without signs of intent. But best fit today is forever. The whole point is to keep score as new data land. What does Avi Loeb get right? 3 things. First, urgency. Interstellar visitors are deadlines with tails. If you don't define tests and run them fast, the object fades and the chance dies with it. Second, specificity. He asks for measurable signatures, distance squared accelerations, thin film polarization, spectral outliers that you can confirm or kill. Third, open hypotheses. Treating technosignatures like biosignatures, possible, testable, falsifiable, is a healthy stance for a field that often meets anomalies with folklore rather than forecasts. Where does he overreach? In moving from anomalous to artificial before natural parameter space is exhausted. Nickel without iron sounds metallurgical, but photochemistry in a carbon-rich coma can plausibly unpair them. A tiny acceleration can appear real until coma-centroid biases are scrubbed. Polarization that looks smooth one night can turn dusty the next under different phase angles. In other words, absence of a clear natural model on day 12 isn't evidence of design on day 13. Extraordinary claims still need multiple, independent, prediction-beating lines of support. Okay, so basically, the consensus today is cautious. 3I Atlas is interstellar, active, CO2 forward, and chemically interesting. Its nickel signal is real enough to chase. Its iron constraints remain soft. Its acceleration, if any, lives in the regime where jets and analysis artifacts fight for credit. That's a lot of science without importing intent. The value of that position is practical. It tells observers exactly what to measure next, and tells theorists what models must hit to stay viable. Here's what would actually change minds, quickly and legitimately. First, a robust, repeatable non-gravitational acceleration that's both too large for the measured gas and dust momentum, and that scales like sunlight pressure, not like jet physics. The fingerprint looks like this. magnitude tracking 1 over r squared within errors, direction staying roughly anti-solar even as activity toggles, and a derived area-to-mass ratio incompatible with any plausible rubblized nucleus. That set would reopen the light sail door, not as an anecdote, but as physics that forces a thin, low-density surface or an unknown natural proxy. Second, a cross-instrument, multi-epoch spectral pattern that defies the best natural pathways. For the nickel puzzle, that means strong, persistent nickel with tight and repeated iron upper limits across changing heliocentric distances, plus failure of carbonyl-based photochemistry models to reproduce line strengths and evolution. Add to that a narrow, stable feature that doesn't map to known cometary or solar lines. If several telescopes at different resolutions lock that in, exotic chemistry gives way to unknown source, and the artificial hypothesis earns serious oxygen. Third, surface scattering behavior that refuses to be dust. Think polarization angles and degrees consistent with specular reflection from smooth, extended surfaces. Light curves with stable, sharp glints that repeat at fixed rotational phases. A phase function that matches thin films rather than porous grains. Dust can fake a lot with geometry, but it struggles to deliver mirror-like consistency over many rotations and viewing angles. Fourth, thermal anomalies with no passive fix. If mid-infrared observations demand internal power at large distances, temperatures too warm for sunlight plus albedo, then you're out of comet country. A constant thermal floor as insulation drops, or a hot spot that tracks neither rotation nor jets, would force either an unknown exothermic process or engineered heat. That's a high bar, but it's clean. Energy budgets don't shrug. Fifth, trajectory intent. We're not talking tiny wobbles. We're talking course changes decoupled from activity signatures, vector shifts that don't process with rotation, velocity steps that appear between quiescent photometric periods, or weak station keeping relative to predictable gravitational features. Even a small, crisp burn like delta V, timed without a corresponding outburst, would vault over natural explanations in a heartbeat. Now, what would not change minds, and shouldn't? Single night anomalies. One spectrograph, S-nickel spike without independent confirmation. A marginal acceleration that shrinks with better coma modeling. An eye-catching image of a straight tail that later spirals under time-lapse. Social posts about anti-solar structures that match textbook radiation pressure when measured. These are the potholes of fast science. You note them, you schedule follow-ups, and you refuse to draw grand conclusions until the data stack. Everything clicked when I realized the decision rule here is Bayesian in spirit, even if we don't write the priors on a whiteboard. Natural comets have a huge parameter space. Thin films and engineered alloys are a tiny corner. Evidence needs to shift weight across that gulf by being both consistent and hard to explain away. The quickest way to do that isn't argument, it's prediction. If a model, natural or artificial, predicts a feature before it's seen, the odds move. So here's the immediate playbook to keep the verdict honest. Observers, lock cadence across optical, near-IR and mid-IR. Measure polarization at multiple phase angles. Push high-resolution spectra that bracket Ni and Phi and track their ratio with distance. And coordinate astrometry with coma center corrections baked in. Theorists publish explicit curves, nickel and iron line strength versus R, expected acceleration vectors versus rotation for jet geometries, thermal flux versus grain size distributions under CO2 dominance. Everyone, pre-register the tests where possible, even informally, so we can judge predictions fairly when the next data drop lands. What this actually means is humility with urgency. Humility, because a lot of impossible comet behavior has yielded to better chemistry and cleaner reductions. Urgency, because we've got a vanishing window to gather the discriminating data. The balance keeps us from getting hypnotized by a single anomaly or numbed by 1,000 plausible patches. If the evidence pivots, clear acceleration without fuel, persistent metallurgical fingerprints, mirror-like polarization. Loeb's framing will look prescient, and the field will have the measurements ready to defend an extraordinary claim. If it doesn't, we still win. We'll have mapped a new corner of comet chemistry, stress-tested our Techno-Signature protocol, and tightened the population models that tell us how often to expect the 4th, 5th, and 6th visitors. One last North Star. The standard of evidence doesn't care about headlines. It cares about repeatability, independence, and predictions that survive contact with the sky. Keep that standard, keep watching 3i Atlas, and be ready to change your mind, either way, when the numbers force it. Watch points and breaking change triggers. Here, what to watch so you can tell in real time if this story shifts. First, new spectral lines or thermal anomalies. If multiple telescopes report persistent nickel with tight iron upper limits across changing distances, that's headline material. Add a mid-infrared flux that won't fit passive dust, temperatures too warm for the sunlight it's getting, and you've crossed into this needs a new mechanism. The actionable cue is simple. Look for coordinated releases from major observatories that show the same features within error bars. Okay, so basically, the second trigger is a confirmed non-gravitational acceleration without matching gas. Not one team saw a hint, but independent astrometry with Comet modeling that still leaves a residual scaling like 1/r², pointing roughly anti-solar, and exceeding what the measured gas and dust momentum can provide. If that lands, you'll see orbital solutions updated with explicit non-gravitational terms and area-to-mass inferences. That's the line in the sand many skeptics set after Oumuamua. Crossing it reopens the light sail argument with fresh numbers. Third, unusual radar or polarization, if geometry allows. Radar is a long shot, but if a powerful dish gets a ping and the echo suggests a large, flat, low-density structure, that's a hardware hint. More likely, polarization will carry the load. Watch for reports of high, mirror-like linear polarization that holds steady across phase angles in a way fluffy dust can't replicate. Pair that with light curves showing sharp, repeatable glints at fixed rotational phases, and you've got a surface scattering case that's hard to dismiss. Fourth, fragmentation events that change the light curve structure. Natural comets fragment often, but the pattern matters. A chaotic breakup leads to a messy, fading swarm with evolving periodicities. Controlled shedding, if such a thing exists, would look cleaner. A step change followed by stable, repeatable photometry and tail morphology that doesn't match random dispersal. Time-resolved imaging will separate corkscrew jet projections from genuine, coherent features. Fifth, data release cadence and provenance. Nobody explains this right, but source matters. Preprints are useful for speed, peer review adds robustness. The fastest trustworthy indicators are coordinated press notes from observatories with data links, overlapping results from different instruments, and quick-look archives you can inspect. Keep an eye on listings from ESO, NASA, JWST, and major spectrograph teams. When 2 or 3 independent pipelines converge, treat the result as real until disproven. Everything clicked when I realized you can build a personal dashboard out of 5 feeds, orbital updates from JPL or MPC, spectroscopy notes from observatory blogs or archive, polarization or photometry threads from ProAm networks, mid-IR snippets from mission instruments, and community reduction reanalyses that replicate or fail to replicate claims. If those feeds agree, the headline stands. If they scatter, hold your fire. Here's the counterintuitive part. A null result can be a breaking change. If iron suddenly appears at predicted strengths as 3i Atlas approaches the Sun, that would deflate the metallurgy anomaly and favor carbonyl chemistry. If the putative acceleration collapses when coma-centroid corrections improve, that's a quiet, decisive win for natural models. Nothing new to report, sometimes, is the new report. Let's translate watchpoints into concrete. If then, triggers you can track. If nickel to iron stays lopsided across distances and instruments, then demand refined photochemical models, or consider non-natural pathways. If acceleration residuals persist after coma modeling and scale like radiation pressure, then compute implied area to mass and compare to thin film regimes. If polarization maps show mirror-like angles and high degrees over many phase angles, then prioritize high-cadence light curves and thermal checks for surface confirmation. If mid-IR flux implies internal power at large heliocentric distances, then move propulsion and waste heat hypotheses up the stack. If fragmentation patterns remain oddly coherent, then investigate rotation-locked shedding versus controlled release scenarios. What about the near-term calendar? Expect staggered releases, quick optical spectra first, near-IR volatiles next, and mid-IR thermal fits lagging by reduction time. Astrometric refinements arrive continuously, but the meaningful updates come when fitters switch from gravity-only to models with standard non-gravitational parameters and still need an extra term. Those are the nights that matter. A quick micro-story to ground this. When a weird asteroid once lit up with a strange phase curve, the rumor mill went wild. Days later, a polarization team posted a small note. The angle followed a dust law perfectly after correcting for phase angle and wavelength. Boom, mystery solved, adrenaline gone, science improved. The moral: wait for the cross-technique check before locking a narrative. Here's a practical checklist you can apply as headlines roll in. Is the new claim replicated by at least one independent instrument? Does the team publish detection limits alongside detections? Are the numbers consistent with the last release within stated errors? Does a model predict the next measurable change with a time frame? Has anyone posted the raw or reduced data for community verification? If you can answer yes to most of those, weight the update heavily. If not, pin it but don't pivot your view. One more watch point that's easy to miss: geometry transitions. As phase angle changes, polarization and brightness laws swing predictably. If a claimed anomaly ignores those swings, treat it carefully. Likewise, as 3I Atlas crosses heliocentric distances where water should dominate over CO2, watch whether the gas mix and thermal emission evolve accordingly. Deviations there teach you the physics or flag something stranger. Okay, so basically, the breaking change triggers are not vibes. They're measurable, repeatable signals that force models to move. If we see acceleration without fuel, mirror-like polarization, thermal excesses, or metallurgical ratios that defy chemistry across time, you'll know the debate just shifted. Until then, the smart money stays on a natural interstellar comet with odd chemistry that's teaching us how to read the next one faster and better. All right, key takeaway and your next move. The key takeaway: 3I Atlas is probably natural, but it's the sharpest live test we've had for spotting genuine technosignatures in the wild. If you want the signal before the noise, subscribe so you don't miss the verified data drops. For your next step, watch our deep dive on how we'd intercept 4I, hardware, timelines, and the exact sensors we'd fly to settle these debates on arrival.